Alright, let's get started. So, last lecture we stopped right here at discussing cost estimation inside the Graph Finder. And I basically argue for you that at the end of the day, it boils down to estimating the size of intermediate query results. Because if you can do that, you can basically estimate the cost of the entire query using a bottom-up approach by estimating the cost of each single operator at the bottom level of your query plan tree. Those operators take base relation as input, so you know the size of input from system catalog. So that's not a problem. And if you can estimate the intermediate size, the size for all intermediate results, literally you know the input size for any operator anywhere in your query plan tree. If you know the input size and the algorithm used for that particular operator, you should be able to estimate the cost of the operator. And then you simply add up the query cost for each operator along this tree-like structure. And you get an estimate for the entire query, right? So, boils down to query size estimation. But query size estimation essentially boils down to the concept we introduced earlier, which is selectivity estimation. If you can do selectivity estimation, you should be able to estimate the size of your operator. So in order to support the estimation of selectivity for arbitrary query, right? So what we do is we require the system, the database kernel, to maintain a number of important information in system catalog. Typically, this information includes the following: number of tuples and number of pages per relation, right? A number of distinct key values for each index. The low and high key value for each index. By the way, the key value here means the search key value for your index. We basically want to know the range of search key values from a particular index. And we also want to know the height of the tree and a number of index pages for each index. These are just some basic form of statistics that the database system maintains. And later on, I will discuss more sophisticated information that database actually require to maintain in order to do query selectivity estimation, such as histogram. So let's start with this basic example, right? So it's a basic select from where block, right? And we're using conducting normal form, canonical terms. Typically, we assume independence among different terms in a conducting normal form. In other words, if you know the selectivity of this term and selectivity of this term, the selectivity for the entire query condition is simply the multiplication of the two selectivities, because you assume independence among these query terms. Of course, you may argue in practice that might not be true, right? In practice that might not be true. I'll give you a simple example. If you want to have a selection condition on age and selection condition on income, is there any correlation between the two? Well, I will argue might not be a strong correlation, but we do have some correlation. For example, if you are younger than 20 years old, your income, typically, your income cannot be that high. Right? For most people we know, their income reached the highest around the age 30 to 40, right? in that period. Of course, this is a really kind of vague correlation, but we do have correlations. So if you know the selectivity on income and selectivity on age, you multiply them together. It doesn't necessarily give you the true selectivity when you combine the two critical conditions together, because they're not independent. Does that make sense? And the only way you can address that problem is to maintain a multi-dimensional histogram, which I will describe later on. For now, we assume that each term from this conjunctive normal form is independent from all the other terms in this conjunctive normal form construction, so that if you can estimate the selectivity for a single term, which is a one-dimensional Curie condition, the critical observation is if you consider only a single Curie term, it basically boils down to a one-dimensional range Curie. If you can estimate that, we simply assume independence among all the terms, we will multiply them together for the time being. Right? Later I will say a few words about how to extend this discussion to multi-dimensional space when Curie terms are no longer considered to be truly independent from each other. Okay? So here are some basic form of Curie selectivity estimation. With what we said from last lecture, from last slide, we can easily derive this relationship right here, which is the cardinality of your result, meaning number of tuples in the output, is essentially max number of tuples from the input multiplied by the product of all reduction factors. Reduction factor is the same as Curie selectivity here. Okay? For example, if you want to do this Curie condition here, you want to estimate the selectivity for this one, which is a particular attribute equal to a constant specified by a particular value. Well, if we assume uniform distribution, this is critical, right? If we assume uniform distribution on the attribute, the selectivity of this is simply 1 over number of distinct values on that attribute. If you assume uniform distribution, it's simply 1 over the distinct number of values in that column. For example, rating equal to 10. If you know you have 10 rating values and rating follow a uniform distribution, the selectivity of this is simply 1 over 10 because there are 10 different rating values. Of course, you may argue in practice, this is not true, right? We all know that uniform distribution rarely happens in practice. In practice, often you have a skewed distribution rather than uniform distribution. How do you handle that? We will discuss that later on. For now, we assume uniform distribution. Right? What if I change the Curie condition to term column 1 equal to column 2? Instead of attribute equal to constant, now the Curie condition is attribute 1 equal to attribute 2. That's my Curie condition. This is somewhat like a join between two tables, right? Whenever you execute a join between two tables, it's basically expressed in this form. Column 1 from table 1 equal to column 2 from table 2. Well, the observation is you can estimate this by viewing this as essentially the following, which is, so how do you estimate this? Well, essentially, this can be translated into let me see, this is the A, okay. Okay, suppose B has n distinct values. That make sense? Right? And the selectivity of each of this is what? It's simply 1 over number of keys on B. Right? The selectivity of this is simply this. By the observation we just made for the column equal to value case. And similarly, you can also convert this to assuming A has n distinct values, right? So this gives you the conclusion that the selectivity of this is 1 over number of keys in A, which is essentially 1 over small n, right? And this is 1 over n. Okay? So which one we should take? Which one we should take? Well, there is another observation which I'm not gonna, I'm gonna skip the proof for you, which is if you assume uniform distribution, you always get, in this case, you always get overestimate. So you should take the smaller of the two. You should take the smaller of the two. So you take the overall estimation is simply the mean of the two, which is essentially 1 over the max of the distinct number of keys. Why it is an overestimate, if you think about it? Well, because at the end of the day, either you go this way or this way, they should give you the same output, right? No matter which way you look at it, it should give you the same output, it's the same curve, right? It's essentially the same curve. So obviously you should go with a smaller estimation, right? Because they all boils down to the same output. What about this particular coordination here? Domain greater than a particular constant value. Well, again, if you assume uniform distribution, this is easy, right? This is not hard to do, which is you take the max value from the possible range of that attribute minus against the value you have, divided by the size of your domain, and that gives you a selectivity estimation. Why is that? Well, if this is your possible domain, right, and you assume uniform distribution, so the records are distributed like this. These are the distribution of the record with respect to this particular value, with respect to this value. Let's say this value is A. And what you're saying is, what's the selectivity for A greater or equal than a particular value, let's say constant C. And let's say C is right here. This is value C. You're basically selecting this range, right? This is selecting this range. And since you have assumed uniform distribution, essentially the number of points in this range versus the total number of points, this divided by this, must be proportional to the length of this interval over the length of the entire interval. Right? So that's essentially the idea we have here. Okay? This is the set of points, right? So that's essentially the idea. Again, you may argue, fine, what if it's not a uniform distribution, for example? What if the data looks like this? Let's say these are income for US population. Okay? Income. This is our income value. This is how much you make. What do you expect this distribution to look like? What do you expect this distribution to look like? I don't know. I think maybe not many people make no income at all. So that's just a simple thing. But you have a lot of people making a lot of low income, and it becomes sparse. Really sparse, and maybe something like that. Okay. Right? So if you ask the same range query, okay, what's the number of people making this much? And obviously, now it's not gonna be proportional to the interval of your query, obviously. So how do we address this? To formalize the argument I just presented to you, I'm going to use the following slides to demonstrate what's going on. And people introduce this concept called histograms to address this problem. And there are one-dimensional histograms and multi-dimensional histograms. For this class, we're going to focus on one-dimensional histogram. And as part of your lab 4, which I will release next week, you will be implementing a histogram and use that to facilitate your work method. So you're going to build a simple work method. There are two types. There are many different types of histograms. And the most common types of histograms are these two mentioned in the slides. One is called equal width, the other is called equal depth. Equal width is actually the simplest form of histogram. So what is an equal width histogram? Okay. What is an equal width histogram? Equal width, as the name has suggested, basically divide your domain. By the way, we're talking about one-dimensional histogram. So given one attribute, like A or B of your choice, right? Could be a composite attribute, by the way. But if it's a composite attribute, meaning 2 or 3 attributes, you just view that as together as a single dimension value. Does that make sense? Okay? It's a one-dimensional setup. Okay? What you do is, for equal width, you simply divide your domain equally and summarize your data distribution using that equal width partition. For example, what do you do? Well, you are given a budget. Let's say K. So you are only allowed to maintain roughly K values to summarize the distribution of your data. You are only allowed to use K values to summarize the distribution of your data. Let's say you have n distinct values, and typically the requirement is K is much less than n. Otherwise, there's no point. You simply remember all the values. Exactly. So I want to use some value K much less than n to summarize the distribution of these values. Equal width basically says, all you do is you basically, this is your domain range, right? And let's see, this is the, and all you do is divide by K. And you define a variable called the width of your bucket, and then you basically use this to partition your space. And then for each, this is what we call a bucket. And for each bucket, you maintain the number of points, number of records for within that bucket. What we call, in this case, it would be 2. The first one would be 2, 3, 3, and 4, something like that. So it's roughly a uniform distribution in this case. Whereas if you apply the same idea here, though, this is, I don't know, like 6, this is like 10, this is like 4, and this is like 1. You follow me? Okay, so that's essentially what we get. And using this structure, why does it help with your selectivity estimation? If you have a query now, if I have a query now, I ask for example, if my C value is here, how do I estimate the selectivity of this? Well, I can simply look at these two buckets over total number of points I have, which is very easy to calculate. So I get this output, right? Do you follow me? Same thing here. If the value C is here, I can estimate that as like that. But this is the ideal case, right? This is the best case scenario for you. Why I say that? Because the value C you use in your query, right, aligned with your bucket boundary, aligned with your bucket boundary, aligned with your bucket boundary. So you get almost a perfect estimation. What if I change my query condition a little bit? I move C to here. Or I move C to here. To be consistent. Then, what do you do now? Look at, in this case, you really don't. First of all, there's several key observations, right? If this value is here, you still know that these two buckets are completely covered by your query because you are looking this way, right? So you know the query output is at least 5, but much less than 15, because you don't fully contain this bucket. The challenge is, where is it? You only have 25 records in total, and this is a variable that's almost half of your total number of possible values, so it's a big variable. It's a big variation you need to make a guess for. You really don't know. Using this histogram, there's no way you can figure this out. There's no way you can figure this out. And typically what people do is, okay, once I'm given a histogram like this, I will assume uniform distribution within a bucket. So what I do is, I take 5 plus this divided by bucket width times the number of points in that bucket. So I assume uniform distribution within that bucket to do estimation. Is this a good estimator? Well, it really depends. If you're lucky, like this, if the whole distribution is uniform within each bucket, it must be uniform as well, then this actually works okay. Or even if the entire distribution is not uniform, but so happen that that particular bucket that overlaps with the query range is uniform, then you are still okay. However, in this case, in the extreme case, I can construct an example where all 10 points within this bucket are actually outside your query range. And then you are off by a lot if you do this. In fact, I can make this case arbitrarily worse by stacking all these values right here as the very end of this bucket, or at the very beginning of the bucket. And then your query range is like this. So you cover almost the entire bucket, but in fact, you are not covering any point. Meaning this value is almost equal to 1, so you estimate there are 10 points there, but actually there are no points whatsoever in your query range. Okay? So that's the downside of equal width histogram. But what's the upside? Well, the upside is simple, trivial to maintain, right? Essentially, to build an equal width histogram, you don't even have to look at data distribution. Data distribution is irrelevant. What do? You simply look at all you need to know is the max and low value of your domain. In fact, many universities use equal width histogram to summarize student grade distribution, right? So typically when you go to any university, they will give you statistics such as number of students, and then they give you something like GPA between 3.5 and 4, between 3 and 3.5, 2 and 2.5, sorry, 2.5 and 3, and 2 and 2.5. And what is this? This is the equal with this one. This is essentially equal with this one. You go to any university, typically they will give you data like this. So what's important to notice here is a totally ignore the true data distribution from the underlying data, but on the other hand, it's very simple to maintain. All you need to know is a budget value k. By the way, you may argue to maintain this histogram, the size is actually larger than k, right? Because you need to know the start and end boundary for each bucket as well as the number of points within each bucket. One observation though is if you know the domain size, meaning the low value and the high values, you don't really need to maintain the bucket boundaries because you can derive that on the fly because they are equal width. So you really just need to maintain one constant per bucket. So size is k. Even if you do maintain the bucket boundaries, fine. It's a order O, big O k, right? It's a constant multiply k, so it's still in the same order, roughly k space. Space is just one consideration though. You do want to minimize space overhead in constructing this histogram, but on the other hand, the smaller your histogram is, the less query overhead it introduces. That's another argument, right? For the fact that you cannot use a too big of k. In the extreme case, of course, if k equal to n, which is the distinct number value you have, what do you get? Well, you get an exact histogram. You get an exact histogram. And that exact histogram essentially is what we call a bitmap. Basically, it tells you in your domain whether a particular value appears or not in your domain for every possible value. Right? So obviously, that's the exact histogram you can hope for. Do you follow me? Follow my argument? In fact, if you know your domain size, if you know your domain is a discrete domain of possibly n values, n is the actual value appear in your database, distinct number value appear in your database, and capital N is possible value from your domain. Typically, you have this way, n must less equal than n. If you just want to remember whether a value has appeared or not, what do? You can use a bitmap of n bit. In bytes, that's only n over 8 bytes to remember whether value has appeared or not. However, that's not good enough though, because you may have things like this. What does this mean? Well, duplicate, right? This value appears multiple times. So in that case, using a bitmap is not good enough. You do need to use n counters. Each, of course, is integer, right? You need to n counter instead of a bit. Really depends on what you want to do, right? Of course, there's if your goal is really to just remember what value has appeared. For example, so Thomas sent me this bug report, so I want to know more about this person. I said, has Thomas bought anything from Amazon? Right? Don't ask me why, I just want to know. And the exact way of answering that question is what? Is you look at Amazon purchase log and look at whether this person has appeared anywhere in the purchase log. But that's a huge set of records you need to go through, right? It's very expensive to maintain an exact histogram for that. So what people do is to use something called BlueFilter for that purpose. And the idea of BlueFilter is to use much less than over 8 bits to tell you whether a particular value has appeared or not. Much less than that. Okay? if time permits, toward the end of the semester, I will discuss a little bit more about this. Okay? So that's equal width. The second argument, the second approach for histogram is what we call equal depths. Is motivated by the observation that we just made on equal width, which is equal width works really well if your data is uniformly distributed, but in practice it is not. Oftentimes it is not. So what we do is the following. So this is the equal width histogram. Right? The height of each bar represents number of items from that bucket. So as you can tell from equal width, all buckets are the same width, but they are potentially different depths. So to address that, what people do is, okay, I can make buckets equal depths, meaning they contain the same number of points, but to do that, I can no longer enforce same width for those buckets. For example, if I want to make sure, and clearly, for uniform distribution, equal width and equal depth are essentially the same. For uniform distribution, right? You can easily prove this. In general, though, equal width and equal depth are different. For example, in this distribution, if I want to do an equal depth histogram, what I will do, I probably will have to like that. 4 buckets like that. Each has roughly 4 or 5 points. Something like that. Like I show right here. Okay? That's equal depth. And equal depth works better than equal width for more skewed distributions. Right? We can still use this idea to do estimation, but this actually still doesn't solve the problem, right? Because if my query range is right in the middle of somewhere in a bucket, I can tell for sure this bucket is completely covered by my query. But how many points within this bucket is covered, I still don't know. But in general, you can argue it works better than equal width. You may still be off by a lot here, but at least you don't, because each bucket has roughly the same number of points, you don't have a case like in equal width where you can be off by so much because there's so many points in a particular bucket when you use equal width approach. So it's better, but it's not like definitely better. It really is a case by case kind of argument. Okay. So I have some illustration for this too. So this is essentially equal depth bucket, and the bar represents the frequency of each value, meaning you may have duplicates, right? This value appears so much, so it forms a bucket by itself. If you look at these two buckets, why they are equal depth bucket? Because if you stack this bar and this bar together, they're roughly equal to this bar. So the total frequency of all items in a bucket must be roughly the same. That's the equal depth approach. And right around the late 90s, so people have been using this histogram for many, many years. Let's say if you have roughly uniform distribution, go with equal width. If you have skewed distribution, go with equal depth. That has been the norm for many, many years. Till late, around 1998. 2 or 3, I forgot how many people are on this, how many authors on this paper. They said, wait a minute. Look at what we are doing for our estimation. What are we doing? What we are doing is to use when there is a query start at middle of the bucket that doesn't completely overlap with the bucket. We basically have to assume uniform distribution in that bucket and use the length of the overlapping part divided by the bucket length times the total number of items in the bucket to estimate how many actually fall within that range, that overlapping range. Even for equal depth bucket, this may still introduce huge bias. Consider, for example, this as example, this bucket as example. What will happen? What will happen? Let me zoom into this bucket and illustrate to you the problem. Okay? The problem is actually as follows. So what is this bucket? This bucket is what it means is you have two values x and y, and this represents the frequency of x, frequency of y. Frequency of x is much greater than frequency of y, but frequency x plus frequency of y roughly equal to that equal depths. Right? What's the problem? The problem is if you have a query coming like this, of course you have other buckets to come. So you have other buckets here, here, so on. Now suppose you have a query coming in, and the query says my query condition is from here all the way here. And I denote my equal depth equal to b. So this is value b. All of these are value b. Right? What happens? Well, these guys are easy, right? Let's say you have 3 buckets here. So from here to here, I know for sure, roughly, I have 3D points. Right? No matter how they are distributed, guaranteed 3D points. What about here? If you look at this particular bucket, this is roughly the half of your bucket length, bucket width. And imagine we actually know what's going on, but in real application, you actually don't know what the bucket looks like anymore, right? So what you have to do is to estimate this as half d. But then you are off by a lot, right? Because this really is a value we can tell this is much less than d, actually much less than even half d. So this is completely off, even with equal depths, right? So how do you address this problem? How do you address this problem? How do you address this problem? Well, the intuition is as follows. This is important, right? In order to understand the next construction, which is called the V optimal histogram, which essentially is the norm in many systems today for maintaining one-dimensional histograms. The idea is actually very simple. The idea is, if you think about what you're doing here, what should you be doing? Well, instead of make each bucket equal depth, what should you be doing? You should make each bucket as uniform as possible. You should make, let me repeat myself, okay? You should make each bucket as uniform as possible. Alright? Let me give you an extreme example, okay? Suppose these are my values. This is the frequency of the values. Suppose they look like this. Well, how many buckets you need actually? I will argue, no matter what the bucket k is given, I should just use one bucket to represent all of them. And what I will remember is, some of them might be slightly higher, some of them might be slightly lower than this. What I will remember is the starting point and the end point, S and E of this bucket, as well as the height of the bucket. I denote that as B. So I only use 3 values to represent this bucket. Versus, okay, if I have another distribution that looks like this. Okay. Like that. What should I do? Instead of equal depth or equal width, I should not use any of those. What I should do is make each bucket as uniform as possible, meaning three buckets like that. That will facilitate this estimator to work really well. You follow me? Yeah? But how do you capture this notion mathematically? How do you capture this notion of how do you translate this into a formal argument? Like somebody argue me, Tom Brady is good. Okay, how good he is? Oh, he's really good. Okay, define really good. He's fantastic. Define fantastic. Right? So you have to define. Like he won 3 Super Bowls in a row. Okay, that's the definition. Here we go. Right, so we have to define this. What do we mean by bucket as uniform as possible? Well, this is equivalent to say minimize the variance of frequency values in any bucket. Right? Is that the same? First of all, in order to understand what I'm saying here, you need to understand what we mean by variance, right? Do you understand what's variance? I'm sure most of you, if not all of you, understand what's variance, right? But I just want to make sure we are on the same page. So let me go back to 101 basics. Right? Let's understand what variance means. So what is variance? The definition of variance is for a population. We are given a population such as F1, F2, F3. The frequency values of n values. They're just some values, not necessarily sorted. They're not sorted. And what's the variance? Well, you take the average. Let me use X. Not necessarily frequency, any population, right? Represent frequency, income, whatever. What you do is you take the average of these values, which is essentially right? And that's the average. And variance of the set X is essentially what? Is if you try to use average to represent this population, how much variation you expect to see. Right? So using that notation, so what we get is and sometimes we even define standard deviation, which is square root of variance. But these two are roughly the same. Okay. The reason we take square is to get rid of this negative effect, right? Because you may have the average may look like this. This is almost 0, but these are negative values, right? So you are really interested in the magnitude, how far you are from the average, rather than the absolute distance between the value that is positive and negative doesn't really matter. You are really looking at the magnitude of the distance from true value to the average. That's why we take the square root. And that's the reason why people define standard deviation, because if you use variance to try to capture how far you are from the average, it's off by a square factor. But if you take square root, it really gives you a rough kind of sense distance-wise, how far you are from the average, either above or below. So what we're going to do is extend this definition to histogram, to bucketization. Okay? So we basically define something like this for each bucket. Then we sum over all buckets. That's essentially the idea. So how we do that? You're given k buckets, right? You input. Let's define this problem formally. So what's your problem? Your problem is your input is what? Is a set of frequencies for n distinct values, and a budget k of k buckets. And what's your output? K buckets, right? So what you need to define is the starting boundary of the first bucket, the starting boundary, sorry, ending boundary of the first bucket as well as the height of the first bucket. And you do this for a bucket with the requirement of must be equal to the starting value. This must be the last value. And they continuously cover your range. In other words, the end boundary of last bucket must be the starting boundary of the next bucket. For continuous domain, right? For continuous domain. For discrete domain, the requirement is what? They differ by 1, right? For discrete domain. Right? So let's consider discrete domain. It's easier to explain, right? But the same idea actually works for discrete domain is easier to describe. Okay, so that's a constraint, right? Of course, what's the if that's your problem, this is it, right? You can arbitrarily choose k boundaries, then you're done. You satisfy the condition. So subject to there's the objective function. What's the objective function? Well, minimize the total variance. Minimize from all buckets. And that translates to minimize, well, essentially, what you're looking for is the set of parameters that minimize, so that's acme, right? Of this is your parameter space. You want to find values for all of them subject to this constraint such that this following value is minimized. What is that value? Well, summation of k bucket, and you all you need to define is variance for each bucket, right? What is variance within each bucket? Square of that divided by number of points in the bucket, right? Which is essentially this. Assuming discrete domains, right? Discrete domains. Remember, we're assuming discrete domain, that's why I can do this. But I need to define what's fj, right? Sorry, not J. Okay? So that's the formulation. The only thing left is how do you solve this problem? Okay, fine, we understand the definition. How do we solve this problem? With this definition, actually, it's easy to see. For example, this bucket, this equal depth bucket, these two will no longer be there. Rather, I will form these two together because that will minimize the variance. And this one will go with the next guy. Do you understand what I'm saying? So intuitively, if you use this formulation, the bucket, the histogram above will be turned into this right here. And how do you solve this problem? Well, I leave that as an exercise for you, but I can give you a hint. The hint is you're going to use something called dynamic programming to solve. Have you heard of dynamic programming? I hope you do. Right? As computer science master students, you better do. Right? So you use dynamic programming to solve this. So the cost of this is roughly, in other words, the running time of this is roughly n squared. N is your Newton size times k. One challenge though is there are a couple of challenges here. Right? First of all, when n is big, you follow me? When n is big, the calculation cost of this is high. Right? So last year, so this is a really cool result came out by an undergrad in MIT. Of course, he did it with a bunch of others, but he designed a new approach. Give you a constant approximation of this process, meaning the bucketization of the histogram the method will produce in the end is within a constant factor, error-wise. Meaning the variance from their histogram is within a constant factor of this best variance you find using dB. So that's their output. And the running time, you know what? Linear time. The paper, I think, I can show you the paper briefly. This is the paper. And this is the undergrad. Okay. I actually sat on the same table with him. I started a conversation. I said, "What do you do?" And he described it, and I was like, "Oh my gosh, okay, that's good to know." And so K histogram, that's what they're talking about in linear time. Okay, linear time. So if you're interested, you should go and read that paper. Of course, in order to understand that paper, you probably need to read about another hundreds of papers. Not necessarily hundreds, but tens or 20 at least, in order to be eligible to understand that paper. Right? So after reading all that, you may not still be able to understand that, but at least you are capable of understanding that. Okay, so that's one challenge which is, in my opinion, addressed by that work from MIT. But there's another challenge, which is this works for one-dimensional data, right? What about two-dimensional space or multi-dimensional space? For example, a location and income always has correlations. People in, if you make 100K in Salt Lake City, that's good income. Not like really fantastic income, that's good income, okay income, right? But if you make 100K in Bay Area, man, that sucks. Seriously. Seriously, if you look at any house, if you don't believe me, go to Zillow and zoom into any house in Bay Area. You won't be able to find any house that's less than $1 million. And $1 million house, you go and you check, it's like 2-bedroom, no yard, nothing. And surprise, it's built 100 years ago. right? So income and the location obviously has strong correlations. That's the argument I'm trying to make. I'm not trying to make you all look mutable, okay? That's not my intention, okay? But what I'm trying to argue is location, and I know many of you are heading to Bear, right? So just give you an alarm. And location and income has high correlations. So if you try to build one-dimensional Histogram for income and for location, you multiply them together to use as selectivity estimation. It won't work. It will not work. It will not work. Does that make sense? It will not work. So what do you do? What do you do? Well, you can try to extend this idea to build a two-dimensional histogram. What that looks like, by the way. The problem looks like following. Now it's a two-dimensional space, and you have points in that two-dimensional space. There are obviously some correlations, and I draw here. Like that, okay? Okay? Now, the problem is what? Is you try to summarize, I mean, there are billions of points here, right? US population, whatever, right? Billions of points. And you want to quickly estimate, given any query, this is A, this is B. How do I answer this query, right? The selectivity for this, right? So essentially I draw a query box. What's the selectivity of this? Or alternatively, what's the selectivity of this? And so on and so forth, right? How do you estimate this? Well, you can use the similar idea we argued. You see, I'm going to give you K buckets. However, these buckets are no longer one-dimensional buckets, they are two-dimensional buckets. So you can partition the space. A simple partition will be just equal partition. In this K equal to 6. Obviously, this is not going to work well because right? So I can make this perform actually that. So if you know that that's what's going on, what should you do? You should use the budget wisely, right? You should use the budget wisely. What you should do is you should allocate more budget right here than in the other space. Maybe like that. Does that make sense? You allocate more bucket over there in the dense region than in the other place. And the objective is still the same. You basically maintain a B value for each bucket, and you try to minimize the variance of each bucket. Sorry, not variance of each bucket, the total variance, the summation of the variance from all buckets. This problem, one dimension we can solve it using dp, right? What about two-dimensional space? Can somebody make a guess? Well, it's tempting to say, okay, one dimension is n squared k, right? Is 3-dimension, 2-dimension, and cube k? Unfortunately, no. The answer is no. Unfortunately, the answer is no. The reason is once you allow in two-dimensional space, you can have bucket formation like this. In one dimension, the reason you can do a dp is you assume you have a k-1 configuration for up to a value n prime. Then you use one bucket for n prime to n. Then you basically test all possible values for n prime in order to decide the best k-1 configuration, and so on and so forth. That's why it's a dp. But in two-dimension, you no longer have this because it's still a two-dimensional space left, and there's still many ways of cutting them. So this dp idea doesn't work. In fact, this is in And it's not as hard as NP though. It's not NP hard. It's sharp P hard. This one. It's sharp P hard. What is sharp P hard? Well, it's really, really hard. It's slightly easier than NP hard, but still very, very hard. So people basically don't have polynomial algorithm to solve this exactly, so they design various approximation algorithms for this. And then you can imagine this problem going to 3 dimension, 4 dimension, and so on and so forth. Okay? There's a deep literature on this, and I will stop right here. Obviously, I won't be able to cover all this stuff. If you're interested, you can read it. Alright, so I think I can skip all these slides because essentially they summarize what I said on the whiteboard. Fantastic. Okay, now we have a fairly good understanding of selective estimation. By the way, the other thing I didn't cover in selective estimation is instead of building histogram, the other thing we can do is sampling, right? You can use sampling to do this. You can use sampling to do this. That's a deep topic as well. I will try to cover this toward the end if time allows. Not towards the end of this lecture, toward the end of the semester. Okay? I will spend some time covering this. Okay? And that's actually a fascinating topic. Okay? Now, what about estimation for joints? Selectivity estimation for joints. Oh, this is really, really hard. Let me tell you, this is really hard. Actually, we are working on, just last year we got actually this year we got the best paper work in Sigma. Our results actually, in my opinion, for the first time show how you can effectively and efficiently estimate the size of the zone. Now, in the past, what people have done? Well, for joint, basically there are many, many different joint problems, right? That's the simplest joint. You can extend this to even more complicated. You can do it and this actually is much harder than this. Why? Because geometry speaking, from a geometry point of view, what is this? You are looking for triangles. These are all the A's, these are all the B's, these are all the C's. Essentially what this drawing does is to find triangles. And Facebook does this all the time. If you are a friend with A, you're a friend with B, whether they're friends. And they are interested in finding out this because why? If you are a friend with me and you're a friend with him, I should recommend them as friends. You go to Facebook, this is really annoying, actually disable this, or they always recommend a friend to you. Essentially, they're doing triangle counting, finding triangles. Of course, if Facebook want to be even more aggressive, you can do what is this? That's essentially of finding squares. But this problem is hard because it could be that colors. So I'm connecting with this guy. They are connected, but I'm not connected. Does that make sense? And this is way harder than, so this, for example, is much harder than if you just draw, both are just involves 4 relations involving 3 drawings, but this is way harder than this. The reason is, in this case, once you start from here, you don't need to go back. You don't need to look back. So each step, which tuple you select is independent from the choice you made before. In this case, it's dependent on the choice you have made before, because you may go all the way down and then finally realize, oh, it doesn't match. So it's much harder. Much harder. So in this class, obviously, again, I won't be able to tell you how to do this, estimate the size of this. order to do that, you need to read this paper. Yeah, this is one of the papers that's related. You basically have to read through all this. And you also need to read this paper. Okay? In order to start having a discussion on this problem. So obviously, to discuss that, I need to have a, I hope the department allow me to have a whole semester class just for that. But maybe nobody will register for that class. That actually is good news for me. Anyway, so we will basically only do this, okay? We'll only do this. How do you estimate this? And we can, to be honest with you, we cannot even really do this. Because even this is not that easy. So we will do a really simplified version of this. Which is, if you don't know anything about your data, you don't know any distribution about your data, you want to estimate the size of your joint, what do you do? Well, you assume uniform distribution. When you assume uniform distribution, it boils down to this, which I have argued for you, but that's just a selectivity. What about the size, the cardinality? Well, the cardinality you simply use, if you go from A to B, if you look at this way, you should use the number of records in R times the selectivity of that. And if you look at this way, you should use the second way of estimating that selectivity, but then multiply the size of the second table. So basically, there are two ways of estimating the joint size. And by my earlier argument, both of them is overestimate, so you choose the smaller one as you estimate for the joint size. So that's why it basically says this. Let me explain this a little bit, right? If you look at R joint S, like column 1 equal to first value of B and second value of B, so on and so forth, that way. If you use that view, what happens is the joint size essentially is total number of records in R, assuming uniform distribution on S, with respect to the joint attribute. What you get is each record in R will match to roughly this number of records in S, which is total number of keys divided by total number of records in S divided by distinct number of values on that joint attribute, because you assume uniform distribution. Do you follow me? And you can do the same using the other view, which is using the number of tuples from S multiplied with number of tuples in R divided by number of keys on this attribute A in R. So you got two estimators, you always take the smaller one, for the reason I have argued. Okay? Now I'm going to show you the results we have produced. So if I change this query just a little bit, currently it estimates the sum, right? But I can change this to count. So what is this table? This table is the same database I showed you last time, which has 140 gigabytes of data. These are the tables, kind of like an algorithm table, right? Like customer, items, what has been ordered. And the problem we have just discussed, which is estimating the size of the joint, is what? Is essentially to execute this group. 146. That's the query we want to estimate, right? The joint size. This is essentially the joint size, right? If you use today's database to estimate this size, go buy a coffee and come back. Literally, I can do that. Or only 100 some gigabytes of data. Okay? And imagine your core automator gonna use this. Wow, that's a really bad core automator. Because you are basically, this is for one plan, okay? This is one plan, you estimate. Wait. And it's not gonna work, right? Not gonna work. Not gonna work. Okay? To convince you it's not gonna work, let's wait a little bit more. Okay? It's not gonna work. Okay? And this is only 100 some gigabytes of data. It's like nothing, right? Google has entire petabytes of data per day. And if you try to ask Google to estimate drone size using this, forget about it. Okay? Forget about it. They will, if you tell them, oh, do this, they might say you're insane. If you try to tell them again, they probably say you should pack up and leave. Right? So it's not going to work, so I cancel it. So look at the system review now. I'm going to change this to count. And I will update this value here. Not this one. I'm looking at this one. Okay. Now I will run this query, right? This is the same query, by the way, connected to the same database. We can immediately give you estimations in real time. And the orange curve is the upper bound of estimate. The light blue curve is the lower bound. And this is the true estimate we'll give you. And what the guarantee is the true size, the estimator, the drone size, the exact value must be within this range. Must be within this range. And you can actually change the way you rerun this. And you can terminate this query at any time if you want to. Okay? So basically, compared to this. Okay? You know what? I will let this run and we continue our lecture, see how long it takes. Alright, so we are done with the discussion on selective estimation. If you want to understand how we did this, you should read one of my papers. It's called Wonder Drone. It's on my homepage. Now, so that's selective estimation. Think about, at the beginning of our discussion on core optimization, I mentioned there are two things we really need to understand, which is, not two things, a couple of things, right? One is to do cost estimation, which we're done, right? Which we're done. And relational equivalence, we're done, right? And what's really left is to find an efficient search plan to go through different, to go through the plan space. The reason you need a search algorithm over the plan space is what I have argued. The plan space is huge. It's basically exponential to the number of relations participating in the drone. Even if you limit to left deep tray only plans, the space is still huge. It's still exponential. So you do need to have an efficient search algorithm in order to go through this massive space. If the search space is small, you don't really need a search algorithm, right? You just enumerate through all possible plans. For each plan, you estimate the cost, you're done. But because the space is so huge, we still need a search algorithm to figure out which plan we actually should consider. And that's essentially the last piece of the puzzle. After this work, I'm really happy we will be done with curve method. This thing is messy and not so easy to explain. And enumeration of alternative plans, there are really two cases, right? Single relation and multi-relation. Single relation is easy because the search space is small. We can actually afford to enumerate all possible plans. Basically try different orders and try the algorithm for each operator, then you're done. Right? Single relation is easy, so I'm going to skip that. Multi-relation. This is hard because you're going to have join, satisfy, commutative, and associative. Satisfy commutative and associative. So you may have a plan like this, and on top of this, each of these operators may use different algorithm too. I may have page oriented, that's loop, and sort or join, and so on and so forth. And each such combination gives you a new plan. For example, page oriented loop here, block and loop here. Or page oriented here, sort or join here, or head join here. Even for the same order, same tree, different combination give you different plans. That's huge. So what we do is we consider only what I argued last time, left deep tree plans. But even in that case, the possible number of left deep tree plans is roughly equal to the permutation of these relations. Right? It's essentially a permutation. Right? And for each permutation, that can be combined with different drawn algorithm as well. So the search space is still huge. So how do we do this? So what people do is to do the following, which is I break this down. I break this down into multiple phases. Phase 1, phase 2, and so on and so forth. What I do is essentially, in high level, what this algorithm does is a greedy algorithm. So what's a greedy algorithm? Imagine it's kind of like has some time with this thing called gradient descent, right? Gradient descent. So if you imagine I throw you into a big mountain range in Utah, and without giving you a smartphone and everything like GPS, nothing. And you look around, it's all big mountains. And how do you get out? Suppose I throw you to the top of Mount Timpanogos, which I just hiked 2 weeks ago. And imagine you cannot see Provo and all the city. You cannot see nothing. It's all you look around, it's all trees and mountains. What do? What's a natural way for you to get out of that situation? Well, you look around. Which slope has a steepest descent, you go along that. Because that's the quickest way to get out of the mountain. You go down and you go to what? A satellite view. Now what do? You go around, you look at, okay, now which slope has the steep angle I should go down that. So you keep doing this essentially. That's essentially gradient descent. That's essentially a greedy algorithm. However, this might not be the optimal algorithm. Right? As you can imagine. Why? Because the mountain may look like this. So this is very steep. So you go this, so you reach a satellite here. But like that. But on this side, it's not as steep as this. So initially you choose this, you go with this DC there. There's a satellite there, but then it's like that. The optimal is to go down this path. But that's if you can do this. If you know the global view, oftentimes you don't. So what do? You choose a local optimal. greedy, right? You're greedy, right? So this is called gradient descent. And this algorithm I'm going to present to you is roughly the same idea. Which I don't have time, so I will stop right here. Before I let you go, I'll show you, hope this code is finished. Unfortunately, it's not finished. But let me show you, we also have, I show you the triangle curve, right? So this, for example, is the triangle curve. And our assistant actually solved that as well. This. Okay, this one. So now Facebook, instead of waiting forever, can now use this system to estimate how many are interfriends between three of them really quickly, in seconds, even with billions of users. Without, get the results back. So let's verify the estimation is actually accurate. So this is roughly about 20 million records, right? What was the estimation we got? Fairly close in that range. Okay? With that being said, I will stop right here and continue. So next lecture, I will finish the discussion on our gradient descent, the greedy algorithm. Then we start something new called transaction. Okay? By the way, I will release homework 3 today. Homework 3 is on core optimization and core evaluation.